Hello, everybody. My name is Dr. Nesha Illich. I'm from Calgary in Canada, and I will be talking to you today about the WebBM, which stands for Web Basin Management Model. This model is a result of about 10 years of development. It is a web application that uses linear programming, and the library of solvers that we use is a publicly available coin.or library. This model is also free to use. It's accessible at www.riverbasinmanagement.com. It is professionally developed using the .NET Core technology, and it also includes the Google Maps interface for schematic representation. There are three solution modes, which include single time step, combined single and multiple time step, and multiple time step optimization. And also, the model can handle variable time step lengths with reservoir and channel routing. This is an important feature that we will highlight in this presentation. There are ongoing applications in Canada, India, and Europe, and the European application is going to be featured in this presentation. The model also has simplified real-time operational mode designed for use by basin managers and reservoir operators. The managers and operators don't need to know how to set up the model. Once it's set up for them, they will be able to use it by updating just the starting storage levels, inflows, or demands, and run it in real time. There is a table here that shows the model components, which is similar to all other basin management models and the associated functions. There is nothing like a specific programming language to use to set up the model, as is the case in most other models. You simply need to develop the input data file, and all of these associated functions will cover 90% of your needs. In most cases, it's very rare to find a basin that we cannot handle with the existing built-in functionalities. What is currently being done in this line of business, whether you're using a simulation model or an optimization model, is you will end up using a model that solves only one time step at a time. And this is bound to create a situation where you run out of water, like it's shown here, and even though you supplied the requested amount for the first half or first third of the irrigation season, once you run out of water and the reservoir is empty, your crop will fail. The only way we can counter this with the current technology is by the use of so-called reservoir rule curves. A reservoir rule curve is a set of target reservoir levels that we do not want to violate. Its shape is provided by the user, and it's typically the same for all simulated years. And its shape also determines how much water will be released as the water is drawn down from one time step to another. The rule curve concept obviously doesn't produce optimal solutions, but it saves you from wasting water in a way that it's shown in this graph. However, the rule curve concept breaks down when you have a sequence of back-to-back dry years, as is shown here, where you would have to be able to refill the storage in order to start from the same starting storage every year. In many years, this is impossible. So once you don't have enough water to start from the target storage, you can't follow these target elevations, and the whole concept breaks down. In order to avoid this concept, at least in planning scenarios, it is better to use the multiple time step optimization approach, where you see, for example, a simple system with one reservoir and one water user, given the inflow of Q1 and the initial storage, and this dashed line will represent the ending storage at the end of the time step. If we now connect this ending storage to the next time step, where there's a different inflow of Q2, this is again the same reservoir, but its starting storage is determined by the ending storage from the previous time step. And of course, the demand may be different in the second time step. We can connect as many time steps as we want in this way. And if we solve the system now, we don't need a rule curve anymore. The model will derive the rule curve. Not only that, but if we add additional constraints, such as, for example, that the supplied amount and the demanded amount have the same ratio in all simulated time steps, then we are going to create a solution that gave us perfect reservoir operation in combination with perfect demand management. Demand management or demand hedging means that we have spread the deficits evenly throughout the irrigation season if we have a dry year and we have to have a deficit. In this particular case, you see the reduction of about 25%, but the model should determine the amount of reduction. It shouldn't be determined by any guessing. So the three solution modes that we talked about earlier, a single time step operation really involves the typical classical use of rule curve or reservoir operating zones, which is a bit better, and it assumes only the foreknowledge of inflows for the current time step. Typically, we use weekly time steps for planning simulation. Now, if you want to do daily time steps, it is usually a good idea to look at the forecast of flows for the next couple of days and do a simulation run where you would have a solution for 5 days, look ahead while you are only adopting the reservoir releases for the very first day. You can move like that for each day and always look at horizon of local runoff and total inflows coming into the system for the next 5 days. This is an improved operation, and it's also convenient for applying the model in real time. Finally, the planning simulations are significantly improved by solving multiple time step optimization for the entire year, or sometimes for all years at once if you're looking at problems where carryover storage from year to year needs to be addressed. Now, you would think that there are many models that can do this, but the truth is there are only three models available right now that can do this multiple time step optimization. These are the Riverware and Oasis. They both come from the United States, and they both cost $50,000 per site. That's the cost of their license. WebVM is free, and neither Riverware nor Oasis can properly handle hydrological channel routing as constraints to optimization. I firmly believe that WebVM is the only available model that can do that at the moment. What this boils down to is, given in an example which you will find in the user manual. If you log on, you can download both the manual and you can look at the instructional videos. The task in this particular problem is to determine releases in day 1 such that the demand is satisfied at day 3. As you can see, the water demand in the first day is 15 cubic meters per second. That's this last line in the matrix here. The second day and third day is also 15 cubic meters per second. And then on the 6th of May, it spikes to 100 cubic meters per second. So we have to increase reservoir releases. Obviously, if we do it on day 3, the water will not get there because there is some travel time involved here. During the low flow period, it takes more than 2 days for it to get there. So you can see the releases in day 1 marked with a red line as they travel through the system day by day, and during day 3 they will have to maintain steady outflow of 16 cubic meters per second, which is the biological minimum, plus the 100 cubic meters per second of demand. So that's a total of 116. So the question that we're posing to the model is, how much should we release in day 1 to provide 116 during day 3? The proper answer is 305. You can see the peak going down from 305 in the first day to 162 and then to 118. And the 118 is just enough to give us 116 at the outlet of this channel in day 3. Why is this required? Because we need to fill the channel storage, which is quite different. If you look at the rating curves and levels that correspond to the average flow of 20 or 30 cubic meters per second, which you will have under normal conditions, to 116, that requires a lot more water in the channel. Most models ignore this constraint, and this is a serious constraint if you want to use the model as a real-time operational tool. The routing equations use the SAR routing method, which is very similar to Muskingum, but it's more sophisticated because it updates the routing coefficients as a function of travel time versus flow. Now we're going to our case study. It's in the Uvac River Basin, which is a tributary of the Drina River on the Serbian side. There are 3 reservoirs and 3 hydropower plants. You can see a very simple schematic here. The legend is given lower left corner of the graph. So each of those hydropower plants has installed capacity, installed flow through the turbines, and the volume of the reservoir upstream of it, and the net head for which the hydropower plant is designed. The idea here is to find out if it was possible to operate these hydro plants better, and in general to find how to operate them better such that they can maximize their power output. We start, of course, by developing the input data. Most studies use some kind of rainfall runoff modeling to provide the inflows into systems of this kind. However, we favor the use of naturalization of flows, which means that in gauged basins where we have reservoir outflows and reservoir levels, we'd like to reconstruct the reservoir inflows as is shown here. So the inflow into this reservoir will be the outflow plus storage change plus net evaporation. And that inflow essentially will be considered as the available runoff for modeling. Let's denote it as R1. For the intermediate catchment between reservoirs 1 and 2, the equation is somewhat similar, but you will see that the total inflow into reservoir 2 is equal to the outflow from reservoir 1 plus the local runoff, and that is equaled with the total outflow, storage change, net evaporation, and any other withdrawals from the reservoirs that may have happened historically. We can assess the R1 and R1 to 2, and these are our estimates of local runoff for every subcatchment that will be important inputs into the model. The other important input is the information about hydropower plants. As you can see from this diagram, the maximum flow through the turbine is a function of water level. Essentially, it's shown as a function of the net head, but the net head, by and large, is dependent on the reservoir storage levels. So as the storage level drops down to about half, so does our produced power. You can see these dashed lines as the lines of equal power, and here we drop from 35 to 30 to 25 to 20 very quick, just by losing about half of the net head. It's very important to specify this constraint to the model such that the model produces a reasonable power. In other words, the maximum produced power is a function of storage, and that relationship should be preserved in the model. Once we developed natural flows or estimates of historic runoff, we conducted this verification scenario where you see that the reservoir was empty for a while, and in this period we were using the recorded flow station in the river, and there was no storage change. The storage change was zero. Once we started filling the reservoir, we had the information about the reservoir outflow, so we were able to actually repeat what happened historically in the model. You see here the comparison between historical and simulated water levels for one of the three reservoirs. For all three of them, we had this kind of match. This has essentially verified our runoff estimates. Now that we have the runoff estimates and also verified the historic production, which we had on the record, but we wanted the model to produce the same amount of hydropower. Once we do that, we can move on to optimization scenarios and look at what could have been done better. And you can see that there is a lot of lowering of the reservoir. This is one of the reservoirs, the middle one, Coking Broad, which has the largest storage. We don't know the reason why this was done historically, but if we kept the water level higher and optimized it for water use, we would only have some times when there was a drawdown, and this drawdown is typically required to make sure that all flows go through the turbines and there are no spills. Indeed, in the best of the runs that we've achieved, there were no spills on any of the three hydropower plants. So what you see in the end is several scenarios that were done with 7-day forecast, 40-day, 14-day forecast, 21 and 28-day. And of course, the longer the forecast, the better the results. In the end, we also show the improvement in the production as a result of both having the forecast and using the model in real-time operation. The total percentages are shown here, and of course the biggest improvement is on the reservoir that I was just showing you. The biggest possible improvement is around 14% compared to historic operation. The total overall improvement is less because we have one of the reservoirs which runs without much variation in head. There's only 7 meters variation in head, and it has a huge head drop of 360 meters of net head. So the improvement there, the maximum possible improvement there is only 5.48%, and yet that's the hydropower plant that has most of the capacity for the whole system. I would like to emphasize that it's possible to improve reservoir operation if this kind of model is used in combination with the reliable runoff forecasting tool. The degree of improvement, of course, will depend primarily on the length of the forecasting time horizon, assuming you're using the WebBM model. For the case of this particular study, we would like to repeat it with daily time step rather than the weekly time step, because we found that the weekly time step is not adequate for mimicking the operation of this system, which is, by the way, very short, and the entire travel time throughout the system is about 1 day anyways. The final note is WebBM offers numerous improvements compared to other existing river basin models, and the authors invite feedback from users around the world. One more screenshot will show you that one of the functions of the model allows you to use the Google Maps to see the solution for any simulated time step, and you can print the solution in either units of flow or units of volume. If you print it in the units of volume, you can easily verify the mass balance for any node, including the complex nodes such as the reservoir nodes shown here. this is all I had to tell you. Thank you very much for your attention.